Hello everyone, I am Morten Tjelta. I'm a research scientist at IFE Norway, and today I'm going to give a presentation called Silica solubility in deep geothermal wells. This work has been carried out under the Deep Scale project. It's an RCN project for 3 years, started in 2019 and will finish sometime next year. It has a total budget of 15 million Norwegian kroners. The topic is deep geothermal flow assurance. And partners are Equinor, GC Node, LedaFlow, SINTEF IFE, ETH Zurich, and NTNU. When we talk about deep geothermal, we typically think of hot fluids usually associated with Iceland. Here, silica scaling is identified as a huge problem. In the picture here, you can see silica scaling from a test well at Iceland, so you can get a feel of the extent of this problem. So today I will talk about IFE's part of this project. And an introduction to the project as a whole was given at a meeting last year. So IFE is going to be responsible for the experimental campaign where we design and establish an experimental setup that can carry out silica solubility experiments at relevant conditions. And I should also mention that we are part of a Horizon EU project called Reflect, which will also use these instruments that I'm going to talk about today. When this project was formulated, we had the IDDP2 well at Iceland in mind. So the temperature range is defined from 300 to 500 degrees C, pressures from 150 bars, which is a typical topside pressure, and up to 350 bar, which is a typical reservoir pressure. The sodium chloride content is from very low and in theory all the way up to seawater. And we want to study slightly acidic fluids. Since we're covering such a wide parameter space, we will come across fluids with different states, from supercritical water here at 500 C and 350 bars, and down to low density gas-like fluids and more liquid-like high density fluids. Also, we need to take into consideration the corrosivity of the fluid itself, because all the components in our experiments need to withstand the conditions. So this is the water dissociation constant as a function of temperature, and you can see that you have a quite high self-dissociation of water somewhat below the supercritical temperature, meaning that in this range you have quite corrosive properties solely from the water phase. So once we had defined the overall parameter space, we went to the literature to find out what has been done before. So this is a scatter point of experimental conditions where we have found quartz solubility data, and the color map here is the sodium chloride concentration. This is a 3D plot of the same points. As you can see, most of the points here are quite blue, meaning that if we take away the pure water points, there are not that many left. So in the 3D figure, then the red points are the one with some salinity. And what this means is that at the high temperature, low pressure side of this vapor liquid equilibrium curve, there are not many data points available. And this is the region, or the optimal region, for deep geothermal energy. So a key step in the experiments in this project is the actual sampling the fluid with a temperature up to 500 degrees and pressures up to 350 bars, because we need to collect the sample in order to analyze it and measure the silica concentration. This is a sketch where this is illustrated. So we have some hot zone and a reactor where we allow a fluid to reach equilibrium with the dissolved silica, and we take that out and mix it with a dilution fluid, which is typically just pure water. And we mix this in a ratio where the diluted fluid is not super saturated. So this figure shows a sketch of the setup design, where I've taken away a lot of details to allow the main message to come through. So this is a hot zone, a furnace, where we have an autoclave with our fluid and silica in equilibrium, and we want to take those fluids out and sample them to analyze it for silica. In order to maintain the pressure during sampling, we have attached what we call a sampling pump, where we allow the same fluid to enter, and it's heated through a coil in the hot zone. And that gives us a fluid sample to this point at constant pressure. So this is where it meets the dilution fluid from the dilution pump. Just pure water with no silica going through a heat coil and diluting the fluid here in this T. That leaves a diluted fluid here, still hot, still pressurized, going out of the hot zone through a cooler, taking it down to room temperature or thereabout, into a pressure regulator, where it is then depressurized from whatever pressure and down to some near ambient, typically 5 bars. And then that pressure goes into a mass flow controller, and we can collect our sample volume at ambient pressure and temperature, and hopefully collect our sample without losing any silica to precipitation during the process. So why do we bother including this dilution stage? Why can't we just sample as simple as possible? So if we look at quartz solubility as a function of temperature at the 350 isobar, this is according to the Akinfeev diamond model, which is the most widely used model for quartz solubility in pure water. And if we then take this hot fluid at 500 degrees C as the starting point, the solubility is just below 0.2 grams per kilogram. And if we were to sample this with constant pressure, it would follow roughly this blue curve, and it would become supersaturated somewhere between 150 and 200 degrees C. But it is widely accepted that quartz kinetics is quite slow. So that means that what you actually precipitate first is the amorphous state, which has a significantly higher solubility, shown here by this black curve. that means that this particular set of conditions could actually be sampled isobaric straightforward, because you will probably be able to collect this fluid at 40 degrees or something. But what's a practical limit for a sample fluid to handle? Well, let's just say it's 100 degrees C. And then the amorphous solubility is about 0.4, indicated by this line, meaning that the fluids in this region are the ones practically suitable for sampling without dilution. But we wanted to build a rig that could sample fluids with somewhat higher quartz contents as well. That's why we included this dilution stage. This is just a table showing the crossing points from that curve. Another reason for including dilution is this region. What happens in this region? Can we be absolutely certain that there is no quartz precipitation? Yes, experience dictates that it is very slow, but that is mainly information from low temperature observations. And it is believed that at higher temperatures, quartz and amorphous silica kinetics actually approach each other. So at some temperature, you will have a precipitation of both, and then you need to consider the quartz limit as well. So to avoid any uncertainties, any confusion, we decided to go for dilution. Based on the considerations described above, we started building. So our initial setup was this Hasloy autoclave. It's inside a furnace, able to take it up to the temperatures that we want. And these are the pumps, the dilution pump and the sampling pump. And on top here we have this sampling rig, and this is actually an air cooler. And behind me there you can see the pressure regulator. So in the initial setup we used quite flexible 1/8 tubing. It's easy to work with, to assemble, disassemble, make new pieces. So this was kind of a proof of concept that we tested up to 300 degrees C. And during those tests we found out that when you start and stop the sampling process, there is quite significant pressure differentials in the system, meaning that the volumes pumped from the pumps is not really what you set them to be necessarily. So we need some kind of way to control our dilution, or to monitor the dilution. So we did some tests with conventional tracers, no silica in the system at all, and it worked quite well. So we found out, well, we need a tracer that can actually be in the experiments, and all our tests are with sodium chloride. So we have tested both chloride and sodium as a tracer, can be analyzed simultaneously with the silica content using ICP. And so this works quite well, and this is what we use now. Of course, we hope that the prototype or the setup version 1 would last, but of course it didn't. In particular, some fittings were not really suited for repeated assembly and disassembly. So we decided to switch to cone and thread fittings for all parts in the hot zone. So we ended up using high pressure valves and fittings. and also some additional alterations. We moved the sampling ports to the side of the furnace, because of course if you take them straight up you may have some cooling and condensation along the walls. Since we now had a much higher temperature, we need the two-stage cooling, and also some other minor improvements to the system. So this is what it looks like now. All the control system is moved outside the room. Autoclave is the same, but the tubings are switched to thicker high pressure tubing. And also some minor modifications, but I like showing pictures. So the results, we did some initial tests at 200 degrees C. They never really reached equilibrium, but our 300 degree tests, they were successful at 86 bars, 1 gram per liter sodium chloride. They were measured at 0.69 grams per kilogram, and the literature value says basically the same. So we hit the target. So with this, we conclude that we have a working system. And unfortunately, that was all that we had time for today. So this is the status, established setup. We believe we are able to do this in a safe way despite the hot fluids. We reproduced literature values. So in the future we will continue with the table that I showed earlier to obtain silica solubility values within this range. And thank you for your attention.